Hello students, welcome to Rao's IAS Study Circles YouTube platform. Today we are going to talk about the Nobel Prize on Chemistry, which was awarded to the scientist for their work on quantum dots. Last week we met and we talked about the Nobel Prize for Physics, and this time we are going to discuss the next Nobel Prize. Now, this platform that we have here, it has been developed particularly from the objective. It has been developed particularly from the objective of ensuring that we are able to share all the details with you, the ones which we are not able to communicate in the lectures at times. It is a platform that gives us a mode of sharing our details, sharing our information with a lot bigger audience. So I want you to give your comments, tell us what all other topics you want, because after the Nobel Prize series gets over, we will be looking for new topics and you guys can be a really good help for that. So let us start with the topic on Nobel Prize 2023. Now, see, so first let me introduce you to the three scientists. Once the introduction is done, then I'll talk about the basics of quantum dots, what is their contribution, how it has been helpful to us. From UPSC perspective, if I consider this, I think knowing what are quantum dots, the basics of it, basics of the nanotechnology on which the quantum dots have been built, and their applications in future would be the three relevant areas from the topic of for UPSC prelims. In mains, you can use the applications part of quantum dots in your various answers whenever it comes to topics related to health, topics related to communications, topic related to fast electronics, technology in general. You can obviously use quantum dots in your answers. So let us start, guys. So the three scientists who have received the Nobel Prize for Chemistry, one is Moungi Bawendi, Louis Bruce, and Alexei Ekimov. Now, Alexey Ekimov is the first person in the, if I go in the chronological order, who has, worked in the area of quantum dots. His work started in the 1970s, but during that time, because he was part of the former Soviet Union, most of the research of Soviet was not easily accessible for the Western world. So that is why his research was mostly unknown for many years. Then Louis Bruce is also another, scientist. His work was mostly associated in the late 1970s and early 80s. His work is also related to the work of quantum dots. And Moungi Bawendi is the scientist from America again, and he has been able to introduce, or he was able to, improve the manufacturing process of quantum dots and how the practical use of quantum dots can be realized. So the purpose for which they have got the Nobel Prize is the discovery and synthesis of quantum dots. Now, just by knowing what are quantum dots, we may not be able to understand and appreciate the topic. So let us first look at the science behind quantum dots. Okay. Now, before I dive into quantum dots precisely, let me first talk about the basics of nanotechnology so that you guys can appreciate the topic here. So all of you understand this word, nanosciences, right? Or you have understood the word, nanotechnology. Now, normally we consider technology is nothing but the application of scientific principles. So that stands true in this case also. Whatever the scientific principles are, when you try to apply them in the real world, they become in general what is technology. So nanoscience and nanotechnology, they go hand in hand like this. Now, when it comes to the world of nanoscience, we have to first understand that nanoscience or nanotechnology, at what realm they really work. So consider this, guys. You guys know that 10 to the power minus 6 meters is what is known as micrometers. What is known as micrometers, right? 10 to the power minus 6 meters. When you talk about 10 to the power minus 9 meters is what is known as nanometers. Nanometers. Right? Now 10 to the power minus 9 is 1,000th of 10 to the power minus 6. So it has been reduced by almost 1,000 times. It has been reduced by almost 1,000 times, and that's how you go from micrometers to nanometers. So basically, nanoscience talks about observing or studying matter, studying different types of substances at nanoscale. So when you observe substances at nanoscale, we call it nanoscalar observations. When you observe substances at microscale, we call it microscalar observations. So nanoscale and microscalar observations, they basically play an important role. They are basically part of our observations here. And microscalar observations are the ones which go around the scale of 10 to the minus 6 meters. That means whatever size of the particle you have, you have started slowing, you have started observing it, you have started shrinking it to a scale of 10 power minus 6 meter. That means it is 1 millionth of a meter. So when you break 1 meter into 1 million components, right, you get 1 micrometer. So when you try to observe substances in a microscalar observation, we call it microscale. When you observe it at, just 1 second, guys. Yeah, sorry for that, guys. So next is 10 power minus 9. So here the observations are 10 power minus 9. That means 1 billionth of a meter. So when you try to break 1 meter into 1 billion components, the single component that is produced, it's called 1 nanometer. So we will revolve, our entire discussion would revolve around these observations only, guys. So I'll go in the background of the things here. Now, in the 1970s, there was a Japanese scientist, his name was Noroi Taniguchi. What is the actual Japanese pronunciation? Please pardon me for that. Right. So Noroi Taniguchi was a Japanese scientist, and in 1974 he coined the word nanotechnology. Basically, what he observed was he was studying gold, guys. He was studying gold, and when he was looking at gold, he observed gold with his, like how visually gold appears. So when you talk about the macro scalar, when you talk about the macro scalar, macro means the macro scalar view is the one that that is visible to our naked eye. So when he was looking at the macro scalar view of the gold, he found out that gold is having that yellow golden color. He found out that gold is having that luster. When the light falls on gold, it starts, creating that sparkling luster. And gold is sonorous. It creates sound. When you hit it, it creates sound. All those physical properties of gold he was able to observe when he was looking at gold at macro scale. So macro scalar observation of gold makes gold appear to have these properties. It is lustrous, it is a good conductor of electricity, it is having this yellow golden color, and it is sonorous, produces sound, sonorous, right? Now, the moment when this scientist started looking at gold and at nanoscale, when he started looking at gold at nanoscalar observation, that means he would put this particular gold in a very strong microscope and would start looking at gold at nanoscalar level. That means 10 power minus 9 meters. At this level, he found out that the properties of gold started behaving differently. Like, the first thing that he discovered was gold's color. The color of gold turned red. It wasn't having the yellow color anymore. At nanoscale observation, the color of gold turned red. In fact, the thermal properties changed. What is the thermal property, guys? Its melting point. Its melting point also started changing. Right? The melting point started decreasing. Right? Other properties also started changing. That means its reactivity also started changing. A lot of these things. By the way, gold happens to be a noble metal, guys. It doesn't react very easily. But at nanoscale, he observed that substances were behaving differently. So when I talk about nanoscalar observation simply talks about that how substances behave at nanoscale. And we have realized that the properties like the melting point, or you can say temperature, responsiveness towards temperature, properties like their optical properties means the kind of light they reflect, the kind of light they refract, the kind of light they emit at certain energy levels. Their optical properties may change, right? Their redox properties may change. Redox is basically the reducing and oxidation reaction, that how far it can absorb oxygen, how far it can release oxygen or absorb hydrogen for that matter. Its chemical reactivity, you can say, that may also change. And on top of that, it may also affect some other properties like their phase, solid-solid transformation, such kind of properties may change. So what we have realized is that when you observe substances at a nanoscale, they behave very differently than what we have so far observed at macro scale. And that is where the world of nanotechnology was started. Now, this field is not a very old field, guys, because it is somewhat related to the invention of quantum physics or quantum particles. And eventually, this field itself got matured we are still often considered as that we are standing at the initial stage of nanotechnology itself. So we often say that the field of nanotechnology is a field that started in the later 20th century, and we are still in the stage of its early development. and the opportunities are going to unravel as and when we study every matter at nanoscalar observations, because substances are behaving at different levels, they are behaving with different properties, and that too at nanoscale. So if we manipulate the nanoscalar properties, we may be able to develop newer kind of materials. So far we have only been able to observe the material property on the basis of their atomic number, on the basis of the electrons that they have. But with nanoscalar observations, we can manipulate those properties further and develop new kinds of substances. Substances having multiple types of melting points at different levels of size with different levels of temperature. We can have substances to have different types of mechanical strength, different types of tensile strength. We can develop substances with different chemical properties. All these possibilities open up when you enter the world of nanotechnology, right? All these things comes up with the simple idea of observing things at the nanoscale. I believe you guys have been able to understand. So I have used a term here called quantum effect. See, quantum effect in general means the effect of observing substances at nanoscale. So the moment when you observe substances at a level lower than 10 to the minus 6 meters, the moment you start observing substances at a size of less than 10 to the minus 6 meter, that means when you start observing substances from micrometers onwards, and that to go further lower to nanometers, then this change in the properties of the matter is called quantum effect. So quantum effect simply talks about the changes that we observe in the properties of the substances when you start observing them from microscalar to nanoscalar observations. And that is the root of all nanotechnological innovations, guys. So remember this, quantum effect is the point for where the nanotechnology was started. And it's very obvious that why this particular field started in the later 20th century, because only by the later 20th century we had the technology to observe substances with such a small scale, at such a small scale. We were not having microscopes, we were not having sensors which could identify properties at such a small level, such a small scale, right? So materials and particles, they attain new size dependent properties. Size dependent property, what do you understand by this term size dependent properties? Now just think about it, guys, just think about it. If I consider a very large substance having this size, suppose there is a cube of this size, right? एक इस size का cube है, right? And I'll compare this. So suppose I take this particular cube and I start heating it. I start heating this. I want to melt it. So what is happening, guys? The surface area exposed to heat is that heat is going to be this particular phases. These are the various phases which are technically going to be exposed to the external heat. So when you apply external heat onto these different surfaces, this much area is right now exposed, and as this area is exposed, eventually what will happen? As these areas will start melting, slowly the entire cube will start melting and down to the innermost particle. So from the external particle to the innermost particle, the substance will start melting, and it will be possible once all these substances, their exposure of heat increases to a level that they start melting. Now let's say I break this entire cube and break it into very small tiny particles of this size. This is one cube, let's say. Another cube, let's say it is the same large cube which has been broken into smaller particles. So what you are seeing here, now if I start melting them, what you will notice that the area of exposure, the surface area that is being exposed to external heat, has now suddenly increased. Can you guys see? The heat is now being applied to all these surfaces at different levels. सारे surfaces पे exposure हो रहा है, right? All these surfaces are being exposed, and now the net area available for heat exposure is much greater here. Right? It is much greater in this case, and that is why we may notice that here the melting temperature would be somewhat much smaller than the temperature here, because here it is a larger matter that is being exposed to heat, but here the overall surface area has got reduced. So here it is very likely that it may have a somewhat lower melting point than this larger substance. So what is this idea of size dependent properties, guys? The size dependent properties are those properties which are dependent on the size of the molecules that you are interacting with. And that is what is going to change at nanoscale. When you observe substances at nanoscale, it is the size dependent properties that changes. It includes the properties like melting point, optical properties, the response towards light, the kind of light that they emit. It also includes the properties related to the chemical activity, chemical reactions, the properties of electrical conductivity. All those things may change, right, at nanoscale. And this gives us a very strong, you can say a very strong impetus, a very strong motivation to develop newer technologies using the same old conventional matter. See, we all know that silver, gold, they happen to be considered as noble elements. They don't react very easily with the surroundings. This is the reason that your old traditional jewelries are made up of gold, and even if they have kept for thousands of years, they will never get degraded. They will not get corroded like iron, right? So gold is a noble metal. So gold doesn't react that easily. But suppose if you want to create a matter made up of gold, which happens to have a higher reactivity. So there comes the opportunity from nanotechnology that we can manipulate the properties by simply shrinking the size of the gold particle to a certain level where its melting points are different, where its reactivity is different, where it may have different kinds of properties. And that makes a world of nanotechnology an entire world of new opportunities, because we are still at the nascent stage of studying matter and their properties at different levels. I hope you guys have been able to understand the science behind nanotechnology. Now let's go on to the next part. So when you talk about size dependent properties, so size dependent properties are mostly the properties like optical properties, melting point, redox reactions, melting points, and these solid phase transition. Solid phase transition basically means that when a substance having the same molecular mass, having the same properties, but still exist in different solid structures, so they can transform from one solid structure to, or one crystal structure to another crystal structure, maintaining the same bulk mass, right? So these are kind of the properties that often changes at nanoscale. I believe you guys are able to get it. Now let's talk about quantum dots for a while. So the Nobel Prize for 2023 has been given particularly for quantum dots. It has not been given on nanotechnology particularly, guys, but it is a part of nanotechnology that involves quantum dots. So let's talk about quantum dots for a while. Now, I'll be ignoring the definition for quantum dots here, and let's see the science behind quantum dots now. I think if you have understood the previous topic, you'll be able to obviously appreciate this topic as well. Now, see, think about it. Think about it, guys. There is a concept of molecular diffraction. There's a concept, or let's not use molecular diffraction for a while. There's a concept called diffraction of light. Now, all of you guys know that light is a type of a wave, and the wave, it travels without a medium. So light can easily travel from sun to earth without any medium. Light is a type of a wave. Now there's a concept called diffraction of light. Diffraction simply means that whenever light passes around a very sharp objects, whenever a light passes around a very sharp objects or very minute edges, when the light passes around very sharp objects, it will not be going straight, guys. It may bend into a different angle. Or you can say that diffraction of light simply means whenever light passes through a tiny slit, a very tiny opening. Slit means an opening. So whenever a light passes in between a slit of a certain wave, if this light is passing through the slit, we'll see this light bending in different directions, guys. We may see this light bending in different directions. So basically the point is that whenever light is made to travel through a tiny opening, a tiny slit, the light is obviously going to get spread, or they will start bending into different directions and may create a different kind of a pattern, right? This diffraction is something that we see quite often around us. When you look at a soap bubble, if you can picture a soap bubble in front of you, a soap bubble is something that is having two layers. One layer is a layer of water and the other layer is a soapy layer. Between the two, it becomes a very tiny slit, and when the sun's light falls on it, it basically bends all the different colors in different directions, and we can see the rainbow like pattern produced over this soap bubble. We can see the same pattern sometimes in specks. Sometimes when you look at a speck and you fickle it under the light, you may observe some different kinds of color impressions are produced on the specks, right? I can't show you right now, but if it is visible to you guys, you may be able to observe, right? If it is being recorded, so you may be able to observe that when the light falls, you may see some different kind of color impressions being created here. So this is also a phenomenon that is caused due to diffraction, because on your specs, there happens to be a thin layer of anti-glare coating, and then there is a glass layer. So between the two, it becomes a very tiny slit of nanometer size, and that eventually, diffracts the light falling onto it. Now the same concept can be applied on substances at nanoscale. So when you talk about nanoscalar observations, quantum dots is a term that we often use for nanoscalar observations. What are quantum dots, guys? Quantum dots are basically semiconducting materials which show unique optical properties. Like I have already mentioned, optical properties, that how the substances changes the quality of light that is being passing through them, how the substance changes the reflected light, how the substance changes the light that they emit. Okay, so quantum dots happens to be such semiconducting materials which happens to manipulate the optical properties when you observe them at nanoscale. So quantum dots normally have a size of 2 nanometers and goes up to 10 nanometers. This is the usual size that quantum dots have. That means they have a size of a very small, group of atoms. Itna chota size hai, right? Like, just to give you an argument, 1 nanometer is just equal to 10 hydrogen atoms. Just 10 hydrogen atoms makes 1 nanometer, right? So 10 hydrogen atoms, and hydrogen is the smallest element in the universe. So you can just imagine that if you place just 10 hydrogen atoms next to each other, what you'll have is just 1 nanometer, right? I hope yes, these are the 10 hydrogen atoms, and what you have is the size of 1 nanometer. So quantum dots happens to be a size of just 2 nanometers to 10 nanometers. So it could be as small as just a few bunch of atoms placed together. That's what quantum dots are. And you can understand, when the size of these particles are so small, their response to light will also be in accordance to those size as well. Like we have just now seen, when the light passes through a slit, it tends to undergo diffraction, it tends to bend. So similarly, light will also be behaving differently when it is passing through quantum dots particles or quantum dots materials of very tiny size, nanometer size, right? By the way, guys, visible light itself has a wavelength. Visible light itself has a wavelength of, like, visible light is Vibgyor. Just for your additional information, it has a wavelength of 380 nanometers and goes all the way to 760 nanometers. So you guys can understand easily, right, that the visible light itself is having a much significant size of its wavelength, and compared to the quantum dots, they are much smaller. Quantum dots are very, very smaller than that. All right, so let's continue from here. So quantum dots happens to be very small, very small nanoscalar materials, mostly made up of semiconducting substances. Semiconductors are like silicon. They do not conduct electricity in their pure form, but when you add some impurities in them, we call them dopants, they become conductors, right? Their performance enhances. That's why the word dopants is being used in that case. All right, but we'll talk about semiconductors sometime later, not in this video, right? So quantum dots happens to be one such material that happens to respond against multiple optical properties when observed at different nanoscale levels. So what happens, guys, now? So quantum dots, like I mentioned, I have taken the definition from Science Direct. Quantum dots are nanometer size luminescent semiconducting crystals and have unique chemical physical properties due to their size and their highly compact structure, right? So what is the science behind quantum dots? We have observed that when you start creating a compact structure, that means you start breaking the substances from a macro scalar to a nanoscalar observation, and that too in nanoscale, you start moving more and more towards smaller size of 2 nanometers. We observe that substances starts responding to different kinds of light. They start radiating their light in different energy bands, and that is what we see when we see a somewhat larger size electrons, when we see a larger size matter which has a much bigger spacing between the two. We will see some low energy radiations getting released, right? And when you travel from a larger size to a bigger size, we see the kind of light reflected, the kind of light that they will reflect or they would emit would be different. So this particular diagram, don't take it in a very literal sense, but take it from a sense that as the size of the slit, as the size of the observation will keep getting smaller and smaller, the energy, the kind of light that they would release would also keep changing. Like just now, as I mentioned, that when you have a very tiny slit made, light behave differently and it gets released in different forms. Similarly, the size of this slit will define what kind of light is going to bend. All right. So mind my words, guys. This would be an easy way for you to understand that quantum dots happens to be such semiconducting materials which have been manipulated at such a small size that they tend to respond, or they tend to emit lights of different energy, or you can say lights of different wavelengths. So depending on the size, you may manipulate what kind of light they may respond. So that is why the definition says that they are luminescent semiconducting material, that they create their own light of different wavelengths depending on the size at which you are observing them. So here you can see in this image, I've taken the image from the Nobel Prize Committee for Chemistry here. So when you throw light on different particles, you may observe all these particles will convert that light into different colors. Of a certain size, it may respond in the form of red color. Of a certain smaller size, it may respond in the form of blue color. So it all comes down to the particle size that you're observing, and the light, when it falls on it, it gets broken, it gets diffracted into different colors. So a larger slit will be able to bend a larger, longer wavelength light. So we'll see a red color here. A smaller slit will be able to bend a smaller wavelength light, but we'll see a blue color on it. So that's how we can easily manipulate the kinds of optical properties we want to emit, or we want to produce from a different quantum substance. So this is basically the basics of the science behind quantum dots. I've given my own definition here. Quantum dots have same structure and atomic composition. So in terms of atoms, it may be the same substance what they have been using. So it may be silicon only, but silicon being used at a very small observational state, they behave and having different exhibits unique properties, and those properties, you guys know, they are size dependent properties of optics, of chemical reactivity and such. So they start showing different size dependent properties. So all comes down to the fact that at what particular size you're observing that particular quantum material. I hope you are able to understand. So if you guys have been able to understand this entire part, please let me know in the comments if you have been able to get it. If you have any questions, I'll be happy to look at those questions also. Right? So this is what we have in the concept of quantum dots. I believe you guys have been able to understand. Now, just to go one step ahead and go a little deeper into the concept of quantum dots, so that you guys can visualize these things in a better way. It is just a different way of understanding the world of nanotechnology in a better way, or also to appreciate this topic of quantum dots. So I'll go to the slide where I have the images of these three scientists, and as I mentioned that these three scientists were involved in the creation of the quantum dot, discovery and the synthesis of quantum dots. Now Alexey Ekimov and Louis Bruce, they both were involved in developments of quantum dots. They were involved in creating the quantum dots first, right? Now they were able to create these quantum dots from cadmium selenide, selenium and cadmium, compound of cadmium and selenium, or they were able to create it with cadmium sulfide, right? Cadmium sulfide, right? So these were the two scientists. They were involved in, sorry, cadmium sulfide is not this, cadmium sulfide, right? Cadmium sulfide, CDS. So cadmium sulfide, cadmium selenide, these were the kinds of semiconducting material that they used, and they used, and with the help of the semiconducting material, changing their temperature, changing their different properties, they were able to create the first quantum dots. But the problem was, this entire method involved a very high temperature, a very, conditions involving very cool, sometimes very cold, absolute zero like temperature. Sometimes it involved conditions which required very high voltage. So the kind of requirements to create those quantum dots was very high, and it was never considered that they could ever be used for any practical purpose. But Moungi Bawendi, he was able to derive a technique to make cheaper and multiple precise quantum dots of static quality, static nature, that can eventually be used for mass production and mass application of quantum dots. And that is why all these three scientists have got the Nobel Prize for 2023. Two of them has got it for their work on discovering the quantum dots. One of them has got on synthesis of quantum dots. I believe you guys have understood. By the way, Moungi Bawendi also worked under Louis Bruce, right? He worked in the same laboratory. Now, coming back into the application of quantum dots. From UPSC perspective, I believe this should be enough. Coming on to the application of quantum dots. So the first application that I believe is something that all of you might be knowing if you have been an active consumer of technology, then you would have definitely heard of something known as QLED displays. Now, QLED displays are basically quantum dot LEDs. They are light emitting diodes created on quantum dots based materials. So this is how the quantum dots, they respond on different types of energy. You can see different quantum dots material, by changing their particle size, they are emitting different kinds of light. So this technique can be effectively applied on our television screens, on our mobile phones, and we have been able to develop the quantum dots LEDs, right? So in a normal LCD structure, you can see that the entire structure happens to be much bulkier. It has more and more components. But with the help of a QLED display, we can reduce the size, we can make them more flexible, we can make them more agile, and also add on a lot of strength, and still make them much lighter than a conventional LCD. So all these kind of flexible displays, all the possibilities of creating a much thinner, much more agile displays, it is possible today with the help of QLEDs, quantum dot LEDs. Then a very fascinating technique which UPSC can definitely ask is in the area of medicine. Now, medicine is one area which is a popular field in which UPSC often asks questions. So here you can see in the area of medicine, we can use quantum dots for illumination of tissue from tumor tissues. Like in this image, you guys can notice that this particular mouse has been injected with some quantum dot based sensors attached with their mapping cells. So you can put any kind of quantum dot sensor, because the size is of very small size, 2 nanometer size. So it is so small that it can easily be attached with your living cells, and wherever you want to observe the movement of the blood, movement of the tumors, or wherever the tumor, size of the tumor, all these things are possible with the help of quantum dot based imaging. We call it the infrared photo detection, diagnostics, and photocatalysis. All these kind of possible applications are there when it comes to quantum dots. So this is something which is a very good example of quantum dots. Then making faster and faster electronics and computers. Now, so far, quantum dot based semiconducting chip, they have already been developed. Apple has already been using quantum dots in making their bionic chip, by making their bionic processors. So this is something which is already catching up. But honestly speaking, I could not find a very easy or a very convincing diagram for it. So I simply took this image. But you can understand fast electronics and computers is definitely one of the possibilities here. We can actually make higher response semiconducting chips. And like, in fact, when it comes to processors, we simply use a kind of a switch there known as transistors. With quantum dots, it may be possible to shrink the size of transistors even further. And in future, if it is ever possible, we may be able to have single electron transistors. In this way, we can reduce the size of a transistor to such an abysmally low level that we may be able to make a much faster set of electronic items, right? So this is something which is being used almost everywhere today. Then some other applications which have been acknowledged by the Nobel Prize committee, it is flexible electronics can be built. We can make even smaller sensors for the body for monitoring different kinds of health standards. We can make solar cells much more slimmer. The solar cells today right now are comparatively slim, but when you talk about the advanced solar cells, the monocrystalline solar cells, so these are the ones which can obviously be further enhanced and further reduced in their size with the help of quantum dots. And lastly, in the area of quantum computing and communication, this is right now just an expected impact that quantum dots may be able to create, but we are not sure. I have so far haven't come across to any such work where quantum dots have significantly helped quantum computing. Quantum computing itself is a very is a field which is in its nascent stage itself, right? Although some developments have happened, but it is still in the nascent stage. So this is everything I believe that is important from UPSC point of view for the topic of quantum dots. And please let us know how did you like this video. Please also write, ask questions, and please also give suggestions for whatever other videos you feel that we should be making here at Rouse. And that's it. All the best, guys. Let me see if some questions have been there. All right. Yeah, Palak, exactly. Palak has mentioned CDs. So CDs also have those diffraction. Yes, that's absolutely correct. There's a thin layer magnetic. There's a thin film of the CD, and it has a plastic coating over it. Between the two, we also have the same diffraction of light. So this would be everything for the topic of Nobel Prize for Chemistry. I believe we should end the session now. All the best, guys. Thank you.